Okay, welcome back. This is 4.1, Calc 1, extrema on an interval. Right? A lot of this is kind of just technical business. Eventually, we want to get you to the high-powered mean value theorem. Right? In order to produce that thing, it's a labor of love. Okay, there's some chains of logic we need to establish, and then we'll have this nice theorem that will tell us something about something, right? um, it can be summed up pretty quickly, though. Essentially, what we're doing at this point is looking for where the derivatives are zero. Okay? So we have some given curve. We know now how to find a function that will tell you the slope of the tangent line at any point on this curve. That function is called the derivative. Okay, so for instance here, we can visually note that the slope of the tangent line to the curve is 0. Okay. Also visually we could tell it's kind of a maximum right here in its own sense. Certainly there could be, this potentiality that something way over here goes above that point. But this in itself is kind of a relative maximum. Okay, and it happens where this happens exactly where f prime of x is equal to 0. Okay? In particular, this would be some c value. Okay? So the deal will be when you're given some sort of function, we'll just take a polynomial such that we know x squared plus, let's say, 4x plus 2 equal this thing right here we know has a minimum. It's some sort of quadratic. I don't know where it hits the x-axis, but it's going to be a happy face quadratic, and it'll have a minimum value at its vertex. Okay, we can figure out what the vertex is, right? So the vertex is, well, I'll take the derivative. So I have f prime of x is 2x plus 4. Set the derivative equal to 0. 2x plus 4, negative 2x equals 4. So x is negative 2. Right. Right. What I'm saying is that thing is the x-coordinate of the vertex. Now, they punished you back in pre-algebra, forcing you to memorize those formulas for the vertex. So what did we say the formula was? So if you have a vertex h comma k, the h-coordinate, the x-coordinate, would be negative b all over 2a, right? And then to get the k-coordinate, we just plop that thing back into the original function. So this is f of negative b over 2a. If we're right about this derivative thingamajig showing us where we have a minimum value, in other words, where the derivative is equal to 0, we'll find the vertex, then this should give us negative 2, right? So if you put in b, this is a is 1, b is 4, c is 2, you'll get negative 4 all over 2 times a, which is 1, so that would be negative 2. And yeah, sure enough, that's what we get. Right? So the point is to find mins and max from, if this was like maybe an intro to calculus course, I would just have students basically set the derivative equal to 0 and solve. And that would give you everything you need to know. Well, kind of, right? Okay. So that's the idea. This isn't exactly the whole picture, though, because you can have functions which are not necessarily differentiable at their minimum values. And we probably, if you went back in your notes and thought about it, there's going to be things like this, which have different left and right hand derivatives, and therefore aren't differentiable at this particular point. But here, right here, is a minimum value. So the deal is our mins and maxes will occur where the derivative is equal to 0, but not only that, it's where the derivative does not exist. Okay? And then there's cases. So here's a min. This case is a min where derivative does not exist. then there's going to be cases where there's neither um, a max or a min at this point. So, for instance, if you had a cubic function and you took a look at this guy's derivative, so y equals x cubed. Maybe I should have labeled this as like y equals absolute value of x minus 2 or something. Right? Over here, y equals x cubed, x to the 1/3, sorry. Its derivative, y prime, is equal to 1/3 x to the negative 2/3, which is the same as 1 all over 3x to the positive 2/3. Okay, so this means that the derivative is not defined at 0, but clearly it's neither a max or a min. Okay, so what they're trying to do here is kind of iron out a method that will allow you to pick out maxes and mins. They say it's going to be, look for the critical numbers, but the problem is the critical numbers won't always give you a max or a min. Okay, so we kind of need to iron that out, and they do that via the definitions in the book. It's very rigorous, but they do that there. So here is, this is like y equals, well, I guess I already wrote it, x to the 1/3. The derivative does not exist at x equals 0, but it's neither a min or a max. Okay. That being said, the one prerequisite that you have to have for a max or a min is just the thing has to be defined. If it's not even defined, then all this other business kind of goes up in smoke. So there's also this issue. For example, here I have something that most obviously does not have a derivative at this particular point. X equals, let's say this is 2, right? F of 2 is not even defined. Obviously, whatever the heck the derivative is, it's not going to be differentiable there either. It's, you know, best case, it's from the left and from the right, it'll have these vertical, you know, vertical tangent lines for so an infinite value for your derivative. So there's no way it's going to be a max or a min, is what I'm getting at. And in order for something to be even kind of considered as a potential candidate for max min, it has to be defined. If it's not defined, then you don't even include it. Okay, so it's like a bunch of little technicalities, but you know, in an intro class, what I would just say, set the derivatives, take the stupid derivative, set it equal to 0, find that thing, and that's going to be our special number. Okay, for these other cases, they won't come up too much, but they will. I mean, you have to take them in consideration. So we'll still need to worry about you know, where the derivative does not exist. So kind of the ultimate example for an intro calc class would be something that's rational. Okay, so say f of x equals x all over x minus 3. Okay, so what is the derivative? F prime of x equals low d high, so low times the derivative of the high minus high times the derivative of the low, all over the low squared. That'll equal x minus 3 minus x all over x minus 3 squared. X minus x, oh great, so what the heck did I do wrong? Doesn't have a derivative. Low d high minus high d low. It's just 1 over x minus 3, are you kidding me? This is what I get for making up something on the fly. I apologize. Low d high minus high, low d high minus high d low. It's negative 3 all over, I don't know, my brain is not functioning today. Negative 3 over x minus 3, there it goes, squared. So how would I find my critical numbers here? It doesn't even look like there's any critical numbers. Basically, this thing must have just the same kind of slope on all of its domain. It's always increasing. anyways, let's take a look at how I would find the critical numbers. And this is turning out to be an incredibly bad example. What I would tell students is to set the numerator equal to 0. And here there's none. And then set the denominator equal to 0. And this is probably going to be more confusing than helpful. But in this case, I would say a potential candidate for a critical number would be x equals 3. The problem with that is the original function is not defined at that point. So there's no way there's going to be a min or a max value there. Okay. All right. So there's a crummy example. Let's look at what the book kind of has with this issue. Okay, so I don't know. Getting an example from the book. So let's look at example 1. And this is part A. I have f of x equaling 9 times x squared minus 3 all over x. Okay, I want to find the value of the derivative at each of the extrema shown in the figure. So they give us a picture here, in this particular case, of this object. And it kind of looks like a, I don't know, like a logarithmic type problem. But they want to know the value of the derivative at this point, which is 3, 2. Okay, so get the derivative. Maybe easier to split it up. So if you kind of butterfly it, so it'd be 9x squared over x, in other words 9x, minus, if you distribute, it'd be 27 over x, so minus 27x to the negative 1. And then the derivative f prime of x is going to be 9 minus, well, it'll be plus now, 27x to the negative 2, which is just 27 over x squared. Okay, so you're looking for where the thing is equal to 0 or where the derivative is undefined, with the knowledge that supposing this thing isn't defined at the place where this thing is not defined, then we don't even consider it. Okay, so set it equal to 0. Clearly, there's an undefined place at x equals 0, but we don't include it because its function is not defined at that point. So there's no way for it to be a max or a min. The thing just isn't even there. There's nothing there. Okay. All right, so I'm excluding this value altogether, and then I'm solving this for x squared. So I'll move, I got 27 negative all over x squared. Did I lose a negative somewhere? Because this doesn't seem like it's going to have an answer. It should have a derivative. I must have screwed something up. Oh, I wrote it wrong. Crapola. All right, so I'm sorry. Sorry. So the guy in the bottom is x cubed. I cannot see very well anymore. Anyways, this would end up being then 9x to the negative 1, and this would be to the negative 3. Okay? And then if I took the derivative, negative 9 all over x squared minus, or rather it'd be plus now, plus 81, 81 all over x to the 4th. Okay. Okay, but again, the x equaling 0 case, we have to exclude that and just set the thing equal to 0, right? So 0 is negative 9 all over. And let's find a common denominator, right? So it'd be multiply top and bottom here by x squared. So the common denominator over x to the 4th. And then plus just 81. Okay. So supposing x is not 0, I can clear out the denominator and just have negative 9x squared equals, well, plus 81 equals 0. Solve this, so negative 9x squared equals negative 81. So x squared equals 9. And then x equals plus or minus 3. Okay? Okie dokie. So it's saying that there's critical numbers at plus or minus 3, and certainly That's what the book had in mind here. I guess they didn't really want me to find this. They just want me to plug x into the derivative here. So let's look at what happens at x equals 3. And what at f prime of x equals 3. And you know, there's supposedly an extreme value here, so we would expect the slope of the tangent line to be 0. So we expect this to be 0. So let's look. I have negative 9 all over 9 plus 81 all over 81. And certainly that's negative 1 plus 1 is 0. Okay. All right, so I don't know. Take the derivative, set it equal to 0, and solve. That's what it comes down to. See if there's any other good examples. I guess we look at number 13. So after a while, these problems just become, you know, do you know how to take a derivative and do some basic algebra? So here we are finding critical numbers. And I've not defined critical numbers yet. Critical numbers will be numbers, let's make sure I don't say it wrong. F has to be defined at C, and a critical number is one such that F is defined at C and either F prime of C is equal to 0 or F is not differentiable at C. Okay, so it's, you know, F is defined. So let's just write F of C is defined. And F prime of C is equal to 0. Or, so there's these two kind of critical numbers. This is the first flavor. Or F of C is defined and F prime of C is does not exist. Okay, so that's the second flavor of critical number. And you can kind of remember them via pictures. So this first case is when you have a maximum occurring or a minimum occurring like that, where the slope is equal to 0. This is the case where the derivative does not exist. So the prime example is the absolute value function, and right there its derivative won't exist because there's a corner there. So they call it a cusp. Derivatives won't work there. But it's still a minimum value. Okay, so there's these two flavors of critical numbers that we're after. There may be more if I sat back and thought about it, but I think that'll get us through the material. So anyways, 13, g of t is equal to t times the square root of 4 minus t, and t is less than 3. Okay. So they've helped us here with the domain. They're you know, implicitly the domain should just be t less than 4, but I think this is going to exclude maybe one of these guys right here. Okay. So anyways, let's get the derivative. So that should be kind of annoying. So you need a product rule. I'll leave t alone and take the derivative of this part. So that's times 1/2 times 4 minus t to the negative 1/2, and then you need a chain rule times the derivative of 4 minus t is negative 1, and then plus t times the square root, then the derivative of t is just 1, so it's just 1 times the square root of 4 minus t. Okay, let's clean that up and rewrite it. So we'll have negative t all over 2 square root 4 minus t, and then plus just square root 4 minus t. Let's find a common denominator, put it all together. So we have negative t times, well, nothing, plus top and bottom of this thing by 2 root 4 minus t. And that'll give us 2 times 4 minus t all over 2 root 4 minus t. Okay, let's clean that up. So I'd have 8 minus 2t, so 8 minus then 3t when all is said and done, all over 2 times the root 4 minus t. So essentially now if you have some sort of rational expression, you set the numerator equal to 0, set the denominator equal to 0, and that'll give you the critical numbers, sort of, right? So 8 minus 3t, set that equal to 0. So negative 3t equals negative 8. So t equals 8/3 is one critical number, I think. And then 2 times the square root of 4 minus t equals 0. Square both sides, so 4 times 4 minus t is 0. So t has to equal 4. Okay, the function is not defined at 4. All right, the original function is, but they've already gone and restricted the domain and said, hey, let's not bother with that. Okay. Okay, so I don't have to worry about this guy at all. Even though it is technically a critical number, it's not technically a critical number. If the function is not defined at this point, it won't be a critical number. Okay. So it would have fallen into this category, right? F of c is defined, but f prime of c does not exist. But f of c is not defined because of the way we've defined our domain. We only consider values less than 3. 4 is not less than 3. Okay, the other guy, this is where the derivative is equal to 0, and that one fits in the domain. Okay, so that'll be our critical number, and we can go on to the next problem. Okay, let's look at a trig guy. So number 15, we have a trig function. H of x is equal to sine squared x plus cosine x on the interval from 0 to 2 pi. Okay, so again, you're taking the derivative. H prime of x is equal to 2 sine x times the derivative of sine x is cosine x plus the derivative of cosine x is negative sine x. Okay. Find the critical numbers. We set it equal to 0. There's no undefined places here. This thing is continuous everywhere. So anyways, I'm going to set it equal to 0, and it's a trigonometric equation, so I'm going to factor it. So I'm going to factor out a sine x, and I'll have 2 cosine x minus 1. Set each factor equal to 0. And solve on the specified domain. So I'm going to do my unit circle here. Sine is 0 at 0, pi, 2 pi, etc. We're not including 0 or 2 pi, so just at pi. X is equal to pi. That's one critical number. And then here, 2 cosine x. Solve that equals 1. So cosine, well, I'm looking for where cosine of x equals 1/2 in this interval. Cosine, the reference angle for 1/2 is pi over 3. And cosine is positive in the first and fourth quadrant. So it'd be pi over 3, and then this guy, so 1, 2, 3, 4, 5 pi over 3. So x is equal to 5 pi over 3, as well as the first one, pi over 3. Okay, so there's our critical values there. Or critical numbers. Okay, the last issue here, which is important for you kind of non-math people, find the extrema on the closed interval. Okay, so it's just like before. You're going to be setting derivative equal to 0. And solving. At the end, though, we're plugging all these critical numbers back into the original function. But not just the critical number. We also have to include the endpoints of the closed interval. Okay, so once you do that, then you just pick off what's the biggest number and what's the smallest number, and then that's it. Okay? Okay, this becomes important later on when you're doing um, the Maclaurin series. I remember seeing it there. So, and it seemed like we were doing it when we were approximating functions with Maclaurin series in Calc 2. So that's kind of where it came up. I'm sure there's other places, but that's where I remember seeing it the most. Okay, so yeah, take Calc 2. You know. Anyways, let's look at some of the problems from the book. Find the extrema on the closed interval. Okay. And it's pretty simple, like I said. Here's 23. We have g of x equaling 2x squared, minus 8x on the interval from 0 to 6. Okay, so what are we doing? We're finding the critical numbers. So the places where the derivative is equal to 0 or the derivative is undefined. Okay, here we have 4x minus 8. It's defined everywhere. We just have to figure out where it's equal to 0. Okay, so we got one critical number. And we also have to check the endpoints. So we're looking for the biggest and smallest value of this thing on that particular interval from 0 to 6. Right, 0 to 6, 1, 2, 3, 4, 5, 6. The critical number is maybe right there. That's going to basically be the vertex of where the vertex is. If you put 2 in here, you get 4 times 2 is 8, minus 16, so negative 8. And so our parabola looks like this. And certainly we probably have a minimum value there, but we don't know where the maximum is, right? So on this interval, the maximum value is probably going to be at an endpoint. Okay, so you have to go into the function and evaluate the original function for the actual heights of the function. Where is the biggest? Where is the smallest? Right. So g of 0, g of 2, and g of 6. Plugging in 0, I get 0. Plugging in 2, I get negative 8. Plugging in 6, I get 24. Okay, so this turns out to be the min, which is the vertex of the parabola. The location of the vertex is 2, negative 8. And then this guy turns out to be the max. So my picture is probably pretty correct, right? It's actually an intersection point right here. And then it goes down to the vertex. And then way up here somewhere at 6, you're going to have the maximum value at the other endpoint of the closed interval. Okay. Let's try one more of those, and then I'm going to talk about the theory. Okay, so here's 29. H of s is equal to 1 all over s minus 2, which I'm going to write as s minus 2 to the negative 1. And we care about the interval from 0 to 1. Okay, so I'm going to take the derivative of s. H prime of s is, bring down the negative 1, and I have s minus 2 to the negative 2. Okay, so in other words, negative 1 all over s minus 2 squared. I got to find where the derivative is equal to 0 and where the derivative is not defined. So h prime of s equals 0. So I just take this, basically you just can take the numerator and set it equal to 0. So negative 1 equals 0. Oh, there is none, right? So that there's no solutions to this problem. In other words, it doesn't have our traditional critical number. So there's none to be found here. Then where h prime of s is undefined, you just take the denominator and set it equal to 0. So I have s minus 2 squared equal to 0. Square root on both sides, s minus 2 is 0, so s is equal to 2. Okay, technically this is then not a critical number because the function is not defined at 2. So we would exclude it for that reason alone, but not only that, it's not even in our interval. Okay, so there's no way to lose here. You just throw it in the trash. All right, so at the end of the day, this function, it seems that it's just always decreasing on this interval. I mean, it seems like it's always decreasing no matter what on its domain, except where it's not defined. So you can expect this scenario going on. I don't know what it looks like, but going from 0 here to 1 on this interval, it's going to be going probably something like that. So, sorry, so probably something like this, right? So at 0, I don't know what it is. I should have been negative 1/2. I should have put down here, but you get the idea, right? It's decreasing because of the derivative is always negative. It's a negative over something squared, which is positive. Negative over a positive is negative. Okay, so the derivative tells you the slope of the tangent line to the curve. This is saying that the slope of the tangent line to the curve is always negative. In other words, the curve is always going down. Okay, so from here to here, it's decreasing. In other words, there's a maximum here and a minimum here, right? That's the way it should be. The max is at 0, the min is at 1. Let's see. So h of 0, I have to check h of 1. There's no critical numbers to check this time. Okay. I'm going back to the original equation, plugging 0 in there, that's negative 1/2. Plug 1 in there and you get negative 1. Okay, and certainly I got what I needed. This is the max, and then this is the min. So there's little tricks as you get better and better at this. You can kind of rationalize out what's going on there. Okay, so that concludes then probably what you need to know as a student to do your homework. The rest of this is just theory. Okay, so from this point on, I just want to iron out the definitions, and this might be a little extra for some people. Okay, but if you're a math person, you definitely want to stick around. Anyways, first off, we're just talking about extrema and the intermediate value theorem. I believe what is it called? The extreme value theorem. Okay, so extrema, in particular, the extreme value theorem. Okay, so this is a theorem we don't prove, we just assume it's true. And basically it says if f is continuous on a closed interval, then f has both a min and a max. Okay, so if f is continuous on a closed interval, then f has both a min and max. Okay, this is not something we prove. Again, I think maybe if you took like advanced calculus, you would go ahead and prove this. But the book will give you an idea of why it's true. And in particular, this closedness here becomes very important. You remember I quizzed you on the strict definition of a limit where we were working with what kind of interval, what was that definition based on. So in here in particular is very important, and the book will show you why. Let's take a look at an example. So this is the first example where the function is continuous, and you see it has both a min and a max. So here the min value occurs at x, so the min and the max. It's a continuous function on a closed interval. Its min value is at the point 0, and the actual value of the min is 1. The max value occurs apparently at 2, and its value is 4. Okay, so that's an example that follows the criteria of the definition. Okay, it's closed and it's continuous. It's continuous on a closed interval. Okay, so here's one that is not on a closed interval, not continuous on a closed interval. It's going down to 1 there. My pen has found a groove underneath my paper. Okay, this guy does not have a min. Well, it has a min, right? It's still, the min is right here. at 1, or at 0. X equals 0, the min is 1. The max value, though, does not exist. There is not one. Right? So the problem is right here. It gets really, really close to 4, but never exactly gets there. And you can play this game where you can say, ooh, well, the max is 3.9. Then I could say, no, I can find a value x such that the y value corresponding to it exceeds 3.9, like 3.99. And then you say, well, maybe 3.999 is the max. Well, I can find an x value such that the y value gives me a 3.9999 or something. And so it's this idea about there's always something in between numbers on the number line, which may be something we take for granted, but if you have two real numbers, suppose x1 and x2 are real numbers, you can always find an infinite number of numbers in between those two numbers, right? So there will exist an x3 such that x3 is in between x1 and x2. Okay, this fact, this kind of, smushedness of the number line allows weird things to occur like this. Or it seems like, ooh, I must have some sort of max, but no, not really, because you can always wedge something in between here and this non-existent point here. There's an infinite number of things in here. So no matter how close you think you are to the max, somebody can find something that's a little bit closer. Okay. All right, so that's the idea. Then the continuity issue. So this is more of the issue of openness versus closedness. The continuity issue you see in this example, this other example in the book. So it kind of looks like it's continuous, but right at x equals 0, it's not. Okay, so there's an open dot there. Yeah, I know. Let's say it's still defined, but it's not continuous. So the problem with this one is there's no min. Okay, min, none. And then the max, yeah, there is one at 4, but okay. So you need to have both things holding for this to work out right. Okay, so there's that. There's this notion of relative extremis. So in general, you could talk about absolute extremes on the interval, on a generic interval, but the book for our definitions and for your homework is working with relative extrema. And this is just the peak of the hill, basically, is what you're looking at, and it's considered to be on an open interval. Okay? So you're working with open intervals, and I'm trying to think if I have an example, a quick example. Well, let's just define it as that. So it's an open, it's on, it's a max or a min value on an open interval. Okay. So, like I said, the book will also talk about global maxes and mins, but in those cases you won't be working with this open interval. Okay. Thirdly, then, the critical numbers, which I've already been talking about, but have not really defined. We have a definition here. First off, the function has to be defined. Let f be defined at C if f prime of C is equal to 0, or if f is not differentiable at C, then C is a critical number of F. Okay. Then we have this theorem 4.2. which basically says if f has a relative max or min, then it's going to occur at a critical number, okay? Which is why we're going through here and finding the critical numbers in the first place, because we want to identify maxes and mins. Okay, so if f has a relative max or min at x equals c, then c is a critical number of f. Okay, so that's why we're doing what we do with the derivatives, setting them equal to 0 and finding their undefined places. Okay, Theorem 4.2 comes along with a nice, a fancy-dancy kind of proof. Okay. So with a lot of proofs, you got to kind of knock them in the cases. You do like a case-by-case exploration. When there's a lot of cases, like 10,000 cases, you could do like a computer proof, which I think is how they proved the four-color theorem. I'm not sure though. I don't remember. And it's not like I really studied it either. So yeah. So anyways, this is a simple case-by-case. There's initially two cases, but in the second case, I believe there's two sub-cases. Okay. So anyways, the proof. And again, what are we trying to do? So there's a supposition. If f has a relative max or min at x equals c, then we want to show that c is a critical number of f. Okay? So maybe even before I do my proof, I should outline what we're trying to do. So if f is a relative max or a min at c, what does that really mean? So again, there's two possibilities, and these will end up being our cases, right? So the first possibility is that f of c is defined, and f prime of c does not exist. Okay, so there's this case one. Oh wait, that's the criteria for the critical. I apologize. There's okay, so that's the crud. I filed that all up. I'm sorry. The cases are based off of differentiability. Okay, so this is what we're trying to show. We're trying to show one of two things. We're trying to want to show, at the end, then it's a critical number. So what does a critical number mean? It means either f of c is defined and f prime of c does not exist, or f of c is defined and f prime of c equals 0. Okay, okay, so we want to show with this supposition, if f has a relative max or min at x equals c, then either f of c is defined and f prime of c does not exist, or f of c is defined and f prime of c is equal to 0. Okay, that's what we want to end up with. Okay. We want to show this. There's two cases. Okay? So case one, either this thing exists or it does not exist. And what thing is that? The derivative. Okay, so that's how we kind of start. We suppose the derivative does not exist. At this particular point, x equals c. So we're supposing also that f has a relative max or min at c. Well, if f has a relative max, or supposing f has a relative max or min at x equals c, this suggests that f is defined at c. Okay. And if you note, then what do I have? Well, I have the derivative does not exist, and I have f of c is defined. Okay, and that's what I wanted to show. F of c is defined, and f prime of c does not exist. Okay, hence it's a critical number. Okay, case 2 is a little bit more complicated. Okay. I already know that case 2 is going to end up with this conclusion. Okay. I've already looked at it, memorized it 20 times over. I know where we're headed. Okay. F of c is defined, and f prime of c is equal to 0. We'll get the fact that f of c is defined via, again, by the fact that it has a relative max or min at x equals c. Okay. So that'll be kind of done. What we'll need to show is that f prime of c is equal to 0. So in this case 2, as opposed to case 1 where we suppose the derivative does not exist, we're supposing now the derivative does exist. Right? Suppose the derivative exists. We'll suppose, furthermore, the function has either a max or a min. At f of c. Okay. So hence we have that f of c is defined. We have half of what we're after. I mean, we have to be after this one, because we've already presumed that f prime of c exists. Suppose the derivative exists. So it's not even an issue of going after this. So like I said, well, I've already seen the proof and all that jazz, but the truth is this is the only possibility in this case. F prime of c is equal to 0 for this to pan out. So somehow we're going to have to show that f prime of c is equal to 0, and again, it turns into a case-by-case analysis. There's only 3 possibilities for the derivative. Okay? There are only 3 possibilities for f prime of c. Right? Either f prime of c is equal to 0, which would be great, or f prime of c is less than 0, or f prime of c is greater than 0. Okay, so we're going to presume, suppose f prime of c is greater than 0. From the strict definition of a limit, and if you remember what this thing means, so we note the limit of f of x minus f of c all over x minus c, which was our sort of alternate definition of a limit, or alternate definition for the derivative. This thing is equal to some value, and we'll presume that value is greater than 0. So if supposing this thing is greater than 0, we could use the strict definition of a limit to kind of bound this object as a function away from the x-axis. Okay, so if this represents some function and it's going towards L, so let's say, well, we just call it the derivative, right? F prime of x, or f prime rather of c, is equal to this thing, which is equal to L. It has to be the case that it's kind of approaching this L value, and from the strict definition of a limit, we can find an interval around our x value such that these values will always be greater than 0, right? So there exists a delta such that for a particular epsilon, we have all x in this interval around delta. I'm sorry, this is getting a little bit more technical than I want. but I don't think it's really explained even at all in the book, such that f of x minus f of c all over x minus c will be greater than 0 for all x in that interval. Right? So the derivative is a function itself. It's just, it's this thing right here that we're taking the limit of. So you can pretend that this thing right here is a graph of some thing, like we're calling it f prime of x. And if you graphed it, you get some sort of line, but or some sort of curve. But for some interval around c, you're going to have y values that are all kept away from the x-axis. In other words, all of the values on the graph from here to here in this box are going to be greater than 0. And you can see they're clearly restrained away from the x-axis. Okay? All these values, all these y values are greater than 0. And what are all those y values? Well, those are these things. Okay? So for all x's in a particular interval, if you have the limit, the derivative existing, you can pull this trick. Okay? So once you have this factoid, you can go ahead and make a conclusion. Basically, suppose x minus c is less than 0. In other words, you're to the left of c. Okay? And in those cases, then f of x minus f of c need to be also less than 0 for this inequality to hold. A negative over a negative is positive. Okay? So in that case, if you just do some addition, add this to the other side, f of x would be less than f of c, and hence f of c, it can't be a minimum. Okay. On the other hand, suppose x minus c is greater than 0, then that forces the numerator to be greater than 0. And so therefore, if you add f of c to both sides, you get f of x is greater than f of c, and therefore f of c can't be a max. So the problem is, if you supposing that the derivative is greater than 0 results in a contradiction, because we've supposed at the beginning that f of c is either a max or a min. Okay? And this is saying that f of c is not a max and f of c is not a min. Okay? So it turns out similarly, supposing f prime of c is less than 0, we have another contradiction in the same sort of flavor. Okay, and these are contradictions because of our initial assumptions. Okay, so the only possibility left then is that f prime of c is in fact equal to 0. And so we have the other case going on here. We know that f of c is defined. It's either a max or a min, and f prime of c is equal to 0. Therefore, it is, in fact, a critical number. So long story short, if a function has a relative max or min, it will occur at a critical number, and that's why we are going crazy trying to find these critical numbers. Okay. Thanks for watching.